Hello and welcome back to this channel once again. In today's video, we are going to look at the topic equilibrium of a particle. In this video, we are going to consider a system of coplanar forces, that is a system of forces lying in the same plane. Now, if a particle is subjected to a system of coplanar forces that lie in the xy plane, then each of the forces can be resolved into its I and j components. So for instance, assuming we have this to be our xy plane, so we have the y-axis and also the x-axis. Now let's assume that we have two forces acting in this plane. So we have this to be F1 and then we have this to be F2. Now what we are saying is that each of these forces can be resolved into its I and j components. So for F1, we have F1 xi and then F1 yj, and then also for F2, we have F2 xi and then F2 yj. So the two forces F1 and F2 can be resolved into their I and j components. Now, for equilibrium to be established, these forces must sum up to produce a zero resultant force. That is, the summation of F should be equal to 0. Now, this can be expressed as summation of Fxi plus summation of Fyj is equal to 0. And for this vector equation to be satisfied, the x and y component forces must all be equal to 0. That is, the summation of Fx should be equal to 0, as well as the summation of Fy must also be equal to 0. Now these two equations, summation of Fx equals 0 and then summation of Fy equals 0, produces at most two unknowns, which are generally represented as angles and magnitude of forces shown on the particle's free body diagram. Now, what then is a free body diagram? A free body diagram is a diagram that shows a particle and all the forces that act on this particular particle. So given a question, the best thing to do is to think of the particle as isolated and free from its surroundings, indicating all the forces that acts on the particle. Then you can move on to solve what the question demands from you. So without wasting much time, let's take a few examples. Now let's take the first example. The crate has a weight of 500 newtons. Determine the force in each supporting cable. So for this particular question, we have three supporting cables, BA, CA, and then AD, and all these three cables are linked together or connected together by a ring in the middle. And we have a crate attached at D. Now we are asked to find the forces in each of the supporting cables. So first of all, let's focus on the crate. Now the crate is said to have a weight of 500 newtons. So assuming we have this to be the crate, we have the weight of the crate acting vertically downwards. So that is W equals 500 newtons. Now this weight is going to exert an upward tensional force in the cable, that is the cable TAD, which is equal to the magnitude of the weight, except that it acts upward. So that even though the two forces have the same magnitude, they act along different directions. So let's assume that the weight force acting vertically downwards has a negative value. So we have negative W plus the tensional force which acts upwards has a positive value, that is TAD, and we say that this is equal to 0. Therefore, the sum of forces along the y-axis is equal to 0. Hence, we say that equilibrium has been established. So at this point, let's investigate the equilibrium of the ring at A. And we are going to do that by drawing a free body diagram indicating all the forces that act on the crate, and we are going to do that on the XY plane. So let's draw the XY plane. So we have this to be the y-axis, we have the x-axis. Now let's indicate all the forces acting on the crate. So we have the weight of the crate acting vertically downwards. We have W equals 500 newtons. That is the weight of the crate. And the upward tensional force it exerts in the cable, TAD, is distributed between the two cables, TC and then TB. Now we have the angle between the negative x-axis and then TB to be 30 degrees. And then here we are provided with a small slope triangle, that is a 3-4-5 triangle. So basically what we are going to do is to calculate the tensional force in TC and also in TB. So applying the equations of equilibrium along the x and y axis. Now let's start off with the x-axis. Now we said that the summation of Fx should be equal to 0. Therefore, let's find the sum of component forces acting along the x-axis. So how do we apply the small slope triangle? Now we know that the x component of TC acts along the x-axis. Now we have 4 corresponding to the value on the x-axis. And we know that cos theta is equal to adjacent over hypotenuse. Therefore, we say that TCX is equal to 4. So that is the adjacent divided by the hypotenuse, that is TC. And then TC also corresponds to 5. Therefore, we say that TCX is equal to 4 over 5 times TC. So this is the value of TCX. Notice that TCX acts along the positive x-axis. Therefore, we still maintain this value as positive. So for TBX, we have TBX acting along the negative x-axis. So this is TBX. And then we have TBY acting along the positive y-axis. So for TC, we have this also to be TCX, and then this to be TCY. Now let's continue. So to find TBX, TBX is simply TB cos 30. Notice that since TBX is acting along the negative x-axis, we need to negate this value. Therefore, TBX is equal to negative TB cos 30. So now let's add the two values, TCX and then TBX, and then equate to 0 according to the equilibrium equation. So we have TCX plus TBX equals 0. TCX can be simplified as 0.8 TC plus negative TB cos 30 equals 0. Therefore, we have 0.8 TC, and then cos 30 gives 0.8660. So we have negative 0.8660 TB equals 0. Now let's make TC the subject. So we have TC equals, we transpose this to the right hand side. So that becomes 0.8660 TB, and then we divide through by 0.8. Therefore, we have TC to be equal to 1.0825 TB. Now let's call this equation 1. So for equation 1, we had TC equals 1.0825 TB. Now let's consider the forces along the y-axis. So for the forces along the y-axis, we have TCY, we have TBY, and then W, which is the weight of the crate. So for TCY, we have TCY acting along the positive y-axis, and that corresponds to 3. So since sine theta is equal to opposite over the hypotenuse, then that is basically 3/5. So we have TCY equals 3 divided by TC equals 5. So this becomes TCY equals 3 divided by TC equals 5. So by this, we can say that TCY is equal to 3/5 TC, and 3/5 is the same as 0.6, so we can basically write 0.6 TC. And for TBY is simply TB sine 30. So we have TBY to be equal to TB sine 30. Notice that all these two component forces are acting along the positive y-axis, and then we have the weight force acting along the negative y-axis, so it means that we are going to negate this value. So we have W equals 500 newtons. Good. So we know that the summation of the forces along the y-axis should be equal to 0. Therefore, we have TCY plus TBY minus W equals 0. Negative because it's acting along the negative y-axis. It's acting vertically downwards. So now let's put in the values of TCY, TBY, and then W. So for TCY, we have 0.6 TC plus TBY is TB sine 30. Now sine 30 is equal to 0.5. So that becomes 0.5 TB minus 500 equals 0. Now we are going to transpose negative 500 to the right hand side. Therefore, we have 0.6 TC plus 0.5 TB equals 500. Now let's call this equation 2. Don't forget that we had equation 1 to be TC equals 1.0825 TB. So we are going to substitute this value into equation 2. So let's do that. So this becomes 0.6. We have TC to be 1.0825 TB, and then plus 0.5 TB equals 500. So 0.6 times 1.0825 gives 0.6495 times TB plus 0.5 TB equals 500. So when you add these two values, that is on the left hand side, you have 1.1495 TB equals 500. You divide through by 1.1495 so that we have TB to be equal to 434.97 newtons. Therefore, we can round this one up to the nearest whole number as TB equals 435 newtons. So this is the value of TB, the tension in the cable BA. Now let's solve for TC. So we have TC also to be equal to 1.0825. Now we are going to multiply this by TB. So we have 434.97. So after multiplying the two values, we are going to get 470.85. Rounding this up to the nearest whole number, we have 471 newtons. This is the value of TC, the tension in the cable CA. Now let's move on as we take the next example. So to example 2, if the mass of cylinder C is 40 kilograms, determine the mass of cylinder A in order to hold up the assembly in the position shown, given that acceleration due to gravity is equal to 9.81 meter per second square. Now for this diagram, we have three cables. We have the cable DE, EA, and then the cable that extends from E through to B to C. Now we are not given the weight of cylinder A. However, we are asked to find the mass of cylinder A. Now we know that weight is given by mass times acceleration due to gravity. Therefore, the weight of A is equal to the mass of A times G. Now we have G to be 9.81. Therefore, we have the weight to be 9.81 times MA. So that is the weight of cylinder A. Now let's focus on the two cylinders. Now since we want to find the mass of cylinder A, then we need to focus on the sum of forces along the y-axis, because we have no business calculating for the sum of forces along the x-axis. So we just need to focus on the sum of forces along the y-axis. Now considering cylinder A, we are going to have the weight of this cylinder acting vertically downwards. So that is WA equals 9.81 times MA. And this weight is going to exert an upward tensional force in the cable EA. So that is going to be TEA. Notice that they have the same magnitude. However, they act along opposite directions. Now let's focus on cylinder C. Now for cylinder C, we have the mass to be 40 kilograms. So the weight of cylinder C becomes 40 times 9.81, and that is equal to 392.4 newtons. So this is the weight of cylinder C. Now at B, there is a pulley. Now the weight of cylinder C pulls this rope downwards, which exerts a tensional force equal to the magnitude of the weight of cylinder C in this cable. And this makes a lot of sense because we have the same cable across the pulley. Therefore, if the weight of cylinder C pulls this cable downwards, then it's going to exert a tensional force of the same magnitude as the weight of cylinder C in this cable. Therefore, we say that the tension in the cable at B is equal to 392.4 newtons. Thus, TB is equal to the weight of cylinder C. Now let's represent this on the XY plane. So on the XY plane, we have the y-axis, we have the x-axis. We have WA to be the weight of cylinder A. So this is WA, the weight of cylinder A, 9.81 times MA. Now we are going to ignore the weight of cylinder C because it is the same as the magnitude of the tension in the cable at B. So we are going to ignore the weight of cylinder C as we introduce the tension in cable B. So this is TB. So at this point, we are going to find the mass of cylinder A. So in doing so, let's find the y component of TB. So the y component of TB is going to act along the positive y-axis. So this is TBY. Now we know that the angle between TB and the positive x-axis is 30 degrees. Now the reason why we are not going to focus on the sum of forces along the x-axis is because in finding the mass of A, we just need the sum of forces along the y-axis. Now let's find the value for TBY, and then we can add that to WA and then find the value of MA. Now since we have TB to be 392.4 newtons, then to find TBY, we have TBY, which is the y component, to be 392.4 sine 30, and that is giving us 196.2. So that is the value of TBY. Therefore, we say that sum of forces along the y-axis is equal to 0. Therefore, we have TBY acting vertically upwards, which is going to have a positive value. So 196.2. And then we have WA acting downwards, vertically downwards. So minus 9.81 MA, and that is equal to 0. So we transpose this value to the right hand side, and then we have 196.2 equals 9.81 times MA. Therefore, we say that we divide through by 9.81. We have 196.2 divided by 9.81, and that is equal to 20 kilograms. Therefore, the mass of cylinder A is equal to 20 kilograms.